All right, Fred, how you doing?
Oh, doing good, doing good.
All right, great. We're going to work on Chapter 14. Are you familiar with Chapter 14?
Well, I looked over it a little bit.
All right. Here we talk about what we call chemical kinetics. All right. And kinetics refers to the rate of a chemical reaction. So when we talk about chemical kinetics, we're talking about the rate of chemical reactions. Now, I don't know if you've ever really thought about it, but we haven't mentioned much the rate of chemical reactions.
I haven't thought about it much.
Now, if you were to think about a chemical reaction where simple chemical reaction A going to B, all right, and you monitored the rate of this reaction over time, right? And there's a couple ways you could monitor it. Maybe you could monitor how much A there is over time, or how much B there is over time, okay? And for example, a chemical reaction might look like this. The concentration of A versus time starts off at some amount and then goes down as time proceeds. The concentration of B has to go up at exactly the same rate because the ratio is 1 to 1. So for every 1 mole of this A that reacts and forms B, you're going to get 1 mole of B forming, right? So the slopes of these lines, if A is a linear relationship like this, then B would have to have the opposite slope, right? Okay, so the rate of the reaction, rate, would be in terms of maybe the molar concentration of either A or B in this case per, I don't know, seconds, minutes, something like that, per time, right? We'll say per second, for example. So the rate of a reaction will usually be provided in some sort of moles or concentration like molar per time, all right, per second. Okay, so the rate or the speed of a reaction can be given in molar per second or molar per time. And if I look at a plot like this where I look at the concentration of A versus time, then the slope of that line, right? If we look at maybe the concentration of B, we can get a positive value here because it's the rate at which it is forming increases, or the amount of it increases over time, so it's a positive rate, right? And again, moles on the y-axis, time on the y-axis, x-axis. The slope of this line, right, would be rise over run, or moles per minute in this case, or if you wanted to do concentration, molar per minute, or molar per second, all right? So the neat thing about a progress curve, we call it, if we could monitor the concentration or the amount of material versus time, then that slope would be the rate of the reaction, okay? Now there's lots of things that affect the rate of a chemical reaction. The nature of the chemical, right? If the resulting bonds are much stronger than the bonds that are needing to be broken, right? In general, reactivity, right? If a chemical is more reactive because of the shape, if the bonds that are going to be broken are readily available to other reactants or to the formation of those products. If we have a chemical reaction like this, C plus A forming B plus D, or maybe just a single product, right? The ability to establish contact with one another is important. C and A have to come in contact with each other, right? And so if they're in solid, if A and C are both solid, then the atoms or molecules or whatever they are here are going to have a hard time coming in contact with each other if they're both solids. And we've talked about this before, and that's why a lot of chemistry occurs in solution, aqueous, right? And that's why we talked about one of our phases or our conditions being aqueous, because a lot of chemistry can occur in aqueous conditions, right? So if both C and A are gaseous, that's a different story, right? Because gases can move very freely in the container that they're in, or in their condition, right? Whether it's not a container or just in the environment or wherever they are, if they're both gaseous. If one's gaseous and one's solid, the gas is still going to have a hard time interacting with much of the solid. It can hit the surface, but not much more. Gaseous and liquid, same thing. Liquid and solid, possibly the same thing. You know, the solid can be kind of surrounded by the liquid, so you can have an increased, surface area, right? So here's an example of
surface
a chemical
area affects
reaction.
the rate of a chemical reaction.
And it's
Here we have some
affected by surface area.
lycopodium powder. I'm going to place a small amount of it onto this ceramic plate. I'm then going to show you with the Bunsen burner flame that this powder really does not burn in the form that we might expect it to burn as a very flammable powder. And yet, when we allow this powder to sift into the flame as a dust, we've increased the surface area around each particle, and the oxygen concentration around each particle increases. Let's do that now.
Okay, so what we see there is the surface area, or the available surface of the chemical that is going to react, significantly changed the rate of the reaction. You see a little browning here that was occurring because the flame was oxidizing that surface. However, when the particles were readily separated from each other and readily available to oxygen, right, then the oxidation could occur much faster.
Why was the sound off?
Oh, that's just the video. The
chemical reaction that you just saw with the
kind of comes
lycopodium
out
powder, where
at
the
a different-
increased rate of the
video-
chemical
audio
reaction
comes out at a
was
different rate
due
than
to
the
the
video.
increased surface area.
Okay. So, another factor that affects the rate of the reaction is the concentration of reactants. And this should be kind of obvious. If I have C reacting with A, and let's say that's occurring in this vessel right here, all right? And I have C reacting with A, so here's my A, and there's a few A's but very few C's, then it's going to take a while for those A's to find the C's, right? So concentration is a major contributor to the rate of a chemical reaction. All right? Temperature is also something that affects the chemical reaction, the rate of a chemical reaction. And if there's a catalyst, catalysts, what they do is they lower the activation energy. Now, the activation energy we haven't talked much about. I'm sure you've heard about it before, though. If we think about the energy of the reactants here, and here is the energy, so this is energy of our products, okay? And we've seen energy diagrams like this before. This reaction is going to release energy, release heat energy, delta H, negative delta H, right? There is what's called, again, an activation energy, an energy that needs to be overcome before the products can form. And if you have a catalyst, what that does is that lowers the activation energy. It doesn't change the energy of the reactants or the products, but it makes it easier for that reaction to occur. And often what happens, a biological catalyst, for example, here's an example of a biological catalyst having a binding site, maybe for C here and a binding site for A here. And because those bind together, when they bind together, you get an adjustment by the catalyst that helps the new bonds form, helps old bonds break, and then out comes B and D. All right? So catalysts will lower the activation energy. All right. Let's watch this video. This is a video of reactions occurring here we have orange balls and blue balls, and they're reacting together. And the product here, right now we have 50 orange balls, 50 blue balls, and no product. Okay? We can control the temperature. We can change different things. And this is out there on the internet. It's nice and fun to do. There's other scripts like this that you can see the effect of the different parameters on the rate of the reaction. If I push play here, and I see that over a certain amount of time, you see some of the black balls appear. Now, not every collision results in a black ball because the temperature, which is the movement, the rate of the movement of the molecules, is set at 20. If I raise it up to 100, now the rate will increase because the collisions are stronger, right? So if I go back down to 20 now, and this time if I increase the amount of one of the reactants, so now there's a lot more oranges, then there's going to be a lot more collisions that occur, and again, the rate of the reaction, even though it's at 20 degrees Celsius, is going to go a lot faster. Here we have, a reaction where all of our yellows are now solid, and blues are, you could think of them as gaseous, or this could be comparable to a liquid scenario as well. And the rate between these two reactants now is going to slow. The rate at which products form from these two reactants is going to slow, even though A is in high concentration, still starts off with 100. The surface area is relatively low, and so the available orange is decreased significantly. Okay, so we're still at the same temperature as we just were, but now we're going a gas with the solid, but the solid is spread out. So this is an example of what? What do you call it when you spread out the solids like this?
That was like that powder, right? Like the, what do you call it? Surface area.
Yeah, that's right. So here I've taken the solid, spread it out, and I've increased the surface area, and that can increase the rate of the reaction. Okay, very good. So, which of the following would speed a rate of reaction? Now, stirring it, dissolving the reactants in water, adding a catalyst, grinding any solids?
I guess all of these, because dissolving the reactants in water, if they're ionic, for sure, right? Adding a catalyst, you said that would speed a reaction, and grinding any solids.
Okay, very good. All of these will increase the reaction. Now, stirring it, if a reaction is already mixed, so if you have A combining with B and both are aqueous and it's completely stirred, then continuing stirring will not actually increase the reaction. But stirring it will increase the reaction if you have, for example, a solid in a liquid, or a solid in a gas, or a liquid, two liquids that are immiscible, right? If there's just a surface, then stirring it will continually change that surface and agitate it. All right. Now, in the previous example, the example we saw here in the beginning, where the concentration of A changes over time linearly, right? This type of a reaction isn't the only way that chemicals can react. Sometimes, because the rate of the reaction is dependent on the concentration of the reactant. So for this example, let's say I have A plus B combining to form C, and I'm looking at how much A there is over time as the reaction proceeds. Well, A and B, this is my initial concentration, and I can see the concentration goes down this could be for either A or B, so we'll just call this A for now. Concentration of A is going down as time goes on. However, the rate of the disappearance of A, which is the slope, so here's the slope of this part of this curve, the slope of this line changes. It changes as the concentration of A changes. So why do you think the slope changes? If in the beginning, the rate at which it's decreasing is represented by this rate, right? But then it's represented by this rate, and then way down here, the rate is even slower. If you were to think about a tangent line being drawn to this curve, why does the rate at which A disappears or the rate at which B disappears, they're going to have the same rate because it's 1 to 1, and the rate at which C appears, if we were to draw that, we would see C appearing quickly but then gradually slowing as the rate at which it appears, right? Why would that be?
Well, you said it was dependent on the concentration, right?
Uh-huh.
So as A disappears, then there's less of it, so A and B, other A's and B's, are going to have a hard time finding each other as their concentration goes down.
That's right. And as the concentration continues to get smaller and smaller and smaller, the rate will get very, very slow. Okay, so this is in this case, we are looking at the concentration of C versus time. All right. So again, the units for the rate are going to generally be in terms of concentration per time, and we usually lean on molar per second. Concentration could be expressed other ways, but we usually are looking at molar concentrations of either reactants or products, and usually reactants. And seconds per second is usually the time, how fast the molar concentration changes versus time. We can measure this rate as the instantaneous rate, meaning the rate right as the reaction begins, or the average rate. So you could try to fit all the points on this line, put a linear fit on there. It would probably end up looking something like that. And that would kind of be the average of all of these rates over time, if you were to look at all these rates, right? You can also look at, I called this the instantaneous rate here. The initial rate is what this is called right here. The instantaneous rate is the rate at any one given point along this line. And if you remember any calculus, taking the derivative of this curve at any given point will give you a line. Excuse me.
Are you tired?
I guess I am a little bit. But that slope of that line at any given point along there can be called can be known as the instantaneous rate. Okay, good. So we've learned a lot about kinetics of chemical reactions, and we're going to learn a lot more. Good job, Fred.
Okay, I didn't do much, but
You'll do more later.